a phenomenon called refraction. After sunset, over calm water, the air cools most rapidly at lower levels. At such times, distant sounds seem unusually loud. This is an example of refraction. Since the portions of sound waves near the surface travel more slowly through the cooler air near the water, their upper portions that would normally be unheard are bent down toward the surface of the water, and the wave is thus focused and strengthened. We have seen how sound originates and how it is transmitted. Let us now see how these compressional waves produce the sensation of sound. They are first collected by the outer ear and directed by it to the eardrum. The eardrum, like any other diaphragm, is influenced by changes in pressure, such as those produced by longitudinal waves in air or other fluid media. Sound waves, therefore, result in vibrations of this eardrum. Beyond the eardrum is a cavity called the middle ear. Here are located 3 small bones which transmit the vibrations of the eardrum to the inner ear. The latter consists of a spiral-shaped cavity filled with a liquid in which the bones of the middle ear set up vibrations. Along a membrane which separates the liquid into 2 parts are located the auditory nerve endings. Due to the structure of the ear mechanism, the vibrations of low pitch excite the innermost nerves, while those of high pitch excite the nerves nearest to the opening into the middle ear. These excited nerve endings transmit the sound impulse along the auditory nerve to the brain. Not until the impulses arrive at the brain do we experience the sensation of hearing. Let us consider the sensitivity of the human ear. In place of loudness, which is subjective, we will use alternating pressure in the sound field, measured in dynes per square centimeter. The audible intensity range of the normal human ear extends from the flutter of leaves to artillery gunfire. The audible frequency range, capable of reception and interpretation, extends from about 20 cycles per second to about 20,000 cycles, a range somewhat greater than that of the piano scale. Individuals differ considerably in their hearing acuteness. Modern electrical reproduction approaches the audible frequency limits of the original sound employed. You now hear my voice under normal conditions of reproduction. I will change the amplification to a lower but unnatural volume. You observe a change in the quality of my voice. The low frequencies appear to be less prominent. Now I will eliminate all frequencies that lie below 300. You notice the unnaturalness of my voice, particularly the vowels, when reproduced under these conditions. Next, I will eliminate the frequencies that lie above 3,000. Again, you notice a change in the quality of my voice, especially in the consonants. Now I will eliminate the low and high frequencies at the same time. In this case, both the vowel and consonant sounds are affected. Note the effect of eliminating the extreme frequencies in the reproduction of music. Another kind of attenuation occurs out of doors. We can identify but a few of the band instruments, distinguishing only those within a limited frequency range. This is because the intervening distance has reduced the intensity of some of the original sound waves to a point where the crowd noise interferes, while some of it has fallen below the threshold of hearing. How different is the sound of a band close at hand when our ears receive the sound waves well above the threshold of hearing and free from interference of crowd noise. We can distinguish the wide range of frequency produced by the instruments. When sound waves are generated nearby in the open air and no reflecting surfaces interfere, the sound waves are transmitted direct and without alteration. When such sound waves encounter an obstruction, echoes are often produced. This is due to the fact that sound waves are reflected by large obstructing surfaces, just as the waves on the surface of quiet water are reflected when they strike the bank. A similar phenomenon occurs indoors. The direct waves are supplemented by successive reflected waves. This is called reverberation. On striking a wall, part of the energy of the wave is absorbed and changed into heat, part is transmitted through the wall, but a sound wave somewhat weakened is reflected. These waves pass back and forth from wall to wall until their energy is dissipated. You have been hearing this explanation under optimum conditions. We will line the walls with a hard, non-absorbing surface. And you hear my voice under conditions of extreme reverberation. The reflected waves pass back and forth from wall to wall many times before they are dissipated. Now you hear my voice in a room where thick, porous material on the walls is absorbing nearly all the sound wave energy. There is virtually no reflection, and my voice loses the live quality characteristic of indoor speech. Curved surfaces in auditoriums are often detrimental to good room acoustics. Such surfaces reflect and focus the sound waves, producing loud echoes that follow the original sound by a fraction of a second, thus interfering with the clear reception of the sound. Our increasing knowledge of sound is constantly contributing to our enjoyment in such ways as the improvement of acoustics in lecture halls and theaters. But it has been the help of electrical advances that has made possible the most important progress in the communication of ideas through sound. Electricity faithfully transforms these fluttering air beats into lightning-fast impulses of controlled amplitude. Thus, sound communication becomes instantly available through the telephone and radio to all parts of the world. And by electrical recording and reproduction,